Okay, so we're back to talk about equilibrium just a little bit more. And today we're talking about applications of Q, or the reaction quotient. So let's jump right into our PowerPoint. Maybe. There we go. And we're going to, as I said, talk about applications of the reaction quotient, or Q. So just a quick reminder of what Q is. Q is algebraically the same expression as K. We can write K only when the reaction is at equilibrium, but we can write Q, which is the reaction quotient, at any point. So Q takes the place of K. It's the same ratio, but it's for any system, whether or not it's at equilibrium. So we simply substitute in those current concentrations of products and reactants into that same expression. So products raised to their coefficients divided by the product of the reactants raised to their coefficients. So what does Q tell us? Well, Q really is a tool for us to be able to use. So we know that if Q is equal to K, then that means our concentrations are at their equilibrium concentrations, and that means the system is at equilibrium. So when Q equals K, the system's at equilibrium. On the other hand, if K is less than Q, Q is greater than K, there's too much product. And so in order to come back to equilibrium, the system is going to shift to the left. So this is just a tool, again, for us to know which way the reaction is going to shift. So it's going to shift to the left. And there's a neat little trick here. If we write K first, then the inequality sign is going to point in the direction in which the system is going to shift. So you notice that I've written K is less than Q, and we can see that that less than sign points to the left. Our equilibrium is going to shift left. If K is greater than Q, then there's too much reactant. And so our equilibrium is going to shift to the right and make more products to bring us back to equilibrium so that Q and K can be the same. So to sum that up, if Q equals K, the system is at equilibrium. If Q is greater than K, the system is going to shift to the left, consuming products and forming reactants until equilibrium is achieved. And if Q is less than K, the system will shift right, consuming reactants, forming products again until we get back to equilibrium. So it's just a tool to tell us which way it's going to shift. So let's look at a couple of practice problems. This one is from the 2014 practice exam. So we're told that we have a 1 liter rigid vessel containing 1.5 moles of phosphorus trichloride, 1 mole of chlorine, and 2.5 moles of phosphorus pentachloride. So it asks how the measured pressure in the reaction vessel will change and why it will change that way as we approach equilibrium at constant temperature. So this is just a matter of dividing 2.5 by 1.5 times 1. So 2.5 over 1.5 is going to be slightly less than 2. So we know that Q is slightly less than 2, K is 6. And so Q is less than K, and that means that it's going to shift to the right, which would make pressure decrease. And so we're looking for pressure will decrease because Q is less than K. Okay, we'll leave this practice problem for class time. Let's talk about how we use Q in an equilibrium equation or equilibrium calculation. So in this reaction, same reaction we just talked about, although it's set up the other way, we have the decomposition of phosphorus pentachloride into phosphorus trichloride and chlorine gas. Q can be used to tell us which direction the equilibrium shift is going to be. So it's going to tell us which of our reactants and products are going to gain and which are going to lose in order to reach equilibrium. So we're given initial partial pressures. Our phosphorus pentachloride is 0.0500 atmospheres. phosphorus trichloride is 0.150 atmospheres, and the pressure of chloride is 0.250 atmospheres. So it's asking us what the partial pressures are going to be at equilibrium. Now, unlike the problems we've been working with, we have partial pressures of all three. We don't have something starting at 0 and another thing starting with some material present. So we don't know just by glancing at this which direction it's going to go. So the first thing that we're going to do is we're going to calculate Q. So Q in this case is equal to the pressure of each of the products divided by the pressure of the reactants. And so we have 0.150 times 0.250 divided by 0.00500. And when we plug all those numbers in, we get that Q is 0.750. So Q is 0.75. Kp, we know, is 2.15. So Q is smaller than K. So that means that we are going to shift to the right in order to make more products so that the number on the top gets larger, the number on the bottom gets smaller, and Q gets larger until it matches K. So our reaction is going to shift right to make more products. So just as with all of our other equilibrium reactions, we're now going to set up an ice table. So I've gone ahead and set up our ice table, and here we know that this is minus X because we know our reaction is shifting to the right. So this would be minus X, and then each of our products is gaining X. And so we can set up our equilibrium, and now we're simply going to plug that into our K expression. This is Q, but same expression. And we're going to solve for X. And we find that X is 0.0272. And from that, we're able to find the pressures of each of our species at equilibrium. So again, in order to use Q in an equilibrium calculation, we're going to write the Q expression, solve, and find out whether Q is greater than or less than K, so that we know which direction the shift will be, so we know where to write the minus X and where to write the plus X. And then we just ice it like we've been doing with all of our other equilibrium problems. All right, that does it for our discussion of Q and K. As always, if you have any questions, let me know.